They are cosmic killers.
They're the end of stars. They're the deaths of stars.
Spectacular stellar detonations.
100 billion times as bright as the sun.
That for an instant outshine a whole galaxy.
The most massive energetic event in the universe since the Big Bang.
Out of this exceptional cosmic catastrophe comes creation. But if one struck near here, life on Earth would cease. The universe, the cosmic crime scene for a most violent and mysterious force. Supernovas. Supernovas, the sensational and exceptional death of stars, produce the biggest blasts in the universe.
Now, only a small minority of stars actually explode, but those that do just go kablam, blowing themselves to smithereens.
Releasing more energy than the sun does in its entire lifetime by more than 1 billion.
The spectacular detonation blasts vast amounts of lethal radiation into the universe.
If a star at the center of the planetary system would go supernova and explode, it would probably wipe out all forms of life in that planetary system. Radiation would basically sterilize all forms of life on any planet in a planetary system.
Like homicide detectives poring over clues to a cosmic crime, scientists use state-of-the-art tools, telescopes, and technology to find supernovas and to solve the mystery of how and why they occur.
It's an interesting thing because the explosion, the event, has already taken place. And then we get these clues which we gather with our telescopes and try to figure out what happened.
As the stellar investigators know, supernovas have a dual personality. They have absolute power to destroy. And at the same time, they are fundamental to creation itself.
When a supernova goes off, the explosion produces a lot of light, but it also produces heavy elements out of the light ones. So, for example, iron or calcium or sodium or any of the elements of the periodic table, those things came from exploding stars that went off before the sun was formed.
The elements produced in these enormous stellar explosions actually make planets, plants, and people.
The calcium in your bones and the oxygen that you breathe were all cooked up in stars and blown out into space. The shock waves from exploding stars can compress nearby clouds of gas and trigger their gravitational collapse so that they begin the renewed process of formation of new stars, planets, and ultimately life.
Thanks to circumstantial cosmic evidence collected, experts estimate that a mighty supernova goes off somewhere in the universe once every single second.
So that's something like 30 million per year, and that's been going on for the last 10 billion years or so of the universe's existence.
Giving us a sense of how big the universe is, in a typical galaxy like our Milky Way, a supernova suddenly occurs only once or twice a century. However, nobody knows when the next one might come.
It's a completely random process, so we have no idea when the next one will occur. It could be tomorrow, could be 5 minutes ago, could be another 100 years. We don't know.
If it is very close, you would see a very bright event in the sky. It could be even brighter than the Venus or the planets or even the moon or maybe even the sun if it's bright enough.
If a supernova is too close to you, it can definitely destroy life. The flash disrupts the atmosphere, burns things up.
astronomers are constantly policing the skies, keeping a wary eye on at least 2 stars in the Milky Way that have the potential to catastrophically explode close to Earth. One that threatens to blow lies in the heart of the Eta Carina Nebula, about 9,000 light-years away.
Eta Carina is one that we know about, which is a very massive star, maybe even 100 times the mass of the Sun, has a very short life, and it could be that the end of that life will take place sometime very soon.
Another star in danger of going supernova is Betelgeuse, a star in the Orion constellation. This seething star is 15 times the size of the Sun. This one is even closer than Eta Carina to Earth.
It's roughly 500 light years away. It'll be a spectacularly brilliant sight, visible even in the daytime.
There's no question Betelgeuse is going to blow up. It could be tonight, for all our ignorance. It could be 10,000 years from now, short on an astronomical time scale. But it could be tonight that we're sufficiently ignorant about it. So it is worth looking at every night to see whether it's blown up.
Not only do the massive supernova explosions create and destroy stars, planets, and people, they also unleash powerful energy in the form of cosmic rays. These highly energetic charged particles strike our planet each and every day. What's more, they have the capacity to alter evolution.
We live in what I call a disturbed galactic ecology. It is a very eruptive, energetic galaxy out there, and our planet is going to get pummeled by that stuff.
Experts say they can and do change life as we know it.
Well, we know that there are genetic mutations that take place when cosmic rays hit living things. It disrupts the DNA inside cells. And if there were a supernova nearby, there could be a lot more cosmic rays, like 100 or 1,000 or 1,000,000 times more than we ordinarily get. If you're the old species, it might lead to your demise, but it also might lead to new species being developed. So a supernova could be an agent of change, and it could be for better or for worse.
Knowing that supernovas have the power to create and alter life makes it imperative that humankind unravel the riddle of what makes these stellar time bombs tick.
What have you got here?
All right, so this is the supernova factory supernova.
The key to unlocking the mystery lies in the detailed analysis of what is ejected into the cosmos by a supernova.
I'm glad this one did not escape our attention because it was a winner. Yeah. It's a great supernova.
Nature has given us this puzzle. It says, well, I make these objects easily, and we as theorists have to figure out how nature does it.
11825, code 6, 105 North Avenue.
As with any crime scene, critical clues are contained in what is left behind. Like a gunshot, hot gases and explosive debris are propelled through space by these deadly stellar explosions.
Just as these gunshots are driving a shockwave, and you can hear this strong noise from the shockwave, it's actually compressing the matter and heating it up. Shockwave in a supernova is doing the same thing.
As these pieces of shrapnel are hurtling very fast through space, they collide with the material around it, and what forms is a shockwave.
The fantastic stellar detonation shoots vast amounts of ballistic supernova evidence, cosmic debris called remnants, into the universe.
So the remnants are produced as the shockwave keeps on moving out through the universe. It actually produces this very picturesque image of the shock moving outward.
The gases that made up that star are ejected at tremendous velocities, 10,000 miles a second, and so they create an expanding shell, and eventually that can become very, very large.
These things go for thousands of years or even tens of thousands of years. So sometimes we can see the site of a supernova explosion tens of thousands of years after the event has taken place.
The high-speed collision of stellar debris in the shockwave produces intense heat and light in wavelengths invisible to the human eye. They include radio, infrared all the way to X-rays, and gamma rays. Fortunately for astronomers, sophisticated space-based instruments like Hubble, Spitzer, and the Chandra X-ray telescope can help the cosmic detectives see them all.
So basically every instrument in every way you can gives you a somewhat different perspective on what's going on. And then you try to put all that together as an intellectual enterprise.
Like a fingerprint, each supernova has a unique pattern, and they can be analyzed in several different ways.
One thing we can do is measure how bright the supernova is, and that's what we call the light curve. The other thing that we can measure that is really helpful is what we call the spectrum. We take the light from a supernova at a telescope, spread it out into a little rainbow using a prism or a grating, and then measure how much light there is at each color or wavelength.
Analysis of that line can tell us lots of interesting things, like the chemical composition of the supernova, the temperature, the pressures and densities of the gases, how quickly they're expanding, and so on.
Information gleaned from the light curve and spectrum reveals distinctions between each supernova.
So it is much like a detective job where you get different clues from the light curve or from the spectrum and try to figure out what kind of star it was, what made it explode, what the products of the explosion were, and what the effects of that explosion might be.
As time goes on, we can see deeper and deeper into what the star originally was, so we can actually get what the composition of the star was at the time it exploded.
By comparing the light curves and spectra from literally hundreds of supernova cases, scientists have been able to classify supernovas into two main types. Type 1a supernova release no hydrogen. The explosions are uniform in size and luminosity. Type 2 supernova release large amounts of hydrogen. The explosions vary greatly in size and luminosity. But why would there be such distinct types of exploding stars? Might they be blowing themselves apart in different ways? Scientists focused their efforts on uncovering the mammoth question: what drives these stellar monsters to destroy themselves? Like bounty hunters looking for bandits, today's astronomers scour the cosmos looking for deadly supernovas. With their keen eyes on the sky, they belong to a long lineage of stellar observers. In fact, the first supernova ever witnessed by man occurred in China in 185 AD, 2,000 years ago.
The Chinese astronomers kept very meticulous records about what they saw in the sky. Specifically, when something new appeared, they recorded how bright it was, where it was, how long it was there.
Using the Royal Chinese records, stellar investigators today have recently found the remnant of this ancient supernova. It is identified as RCW86 and is in the constellation Centaurus, near two bright stars known as Alpha and Beta Centauri. 1,400 years after the Chinese discovery, the first European observer witnessed a supernova. On November 11, 1572, 26-year-old Danish astronomer Tycho Brahe was taking a walk when he witnessed a shocking stellar phenomenon in the northern sky. It was right next to the W etched by the brightest stars in the constellation Cassiopeia.
Even though he saw it, and even though he was the leading astronomer of his age, he did not believe the sense of his own eyes.
A few years after Tycho's remarkable sighting, his former pupil, Johannes Kepler, made his own groundbreaking observation of a new star.
he measured from star to star around it the distance. And we can use that now to recreate exactly the position of where it exploded.
When contemporary investigators took a closer look at Kepler's 1604 remnant, they found something very strange about it. A detailed analysis of the chemical composition of the ejected and expanding gases indicated that there were two stars that somehow conjoined to produce a gigantic explosion. So how did this companion cause the stellar catastrophe?
Many stars are in binary systems, so they have a partner that is orbiting around them. And we think what happens is that one star puts mass onto the other.
Experts have since found that the companion, or binary scenario, is the hallmark of what is called a Type 1a supernova.
The Type 1 supernovae, we think, are the explosion of white dwarfs. So a star like the Sun will produce a little dense nugget about the size of the Earth.
When a star like the Sun dies, it ejects its outer layers and leaves behind just a small, dense, burnt-out core called a white dwarf.
The ashes of the Sun will be a carbon and oxygen white dwarf. Left to its own devices, that will just last forever and cool off.
But when a star has a companion, like a partner in crime, it can lead to catastrophe.
One star puts mass onto that white dwarf, pushes its mass up to the point where it becomes unstable, and that there is burning that takes place in the center. And very, very rapidly, the star goes from being a kind of boring white dwarf to being a tremendously violent and brilliant supernova.
But why do some white dwarfs catastrophically explode? That was figured out in 1930 by a brilliant young astrophysicist, Subrahmanyan Chandrasekhar, the Sherlock Holmes of astrophysics, on a boat trip from India to England.
During this long voyage, he used the newly developed fields of quantum physics and special relativity to come up with the idea that a white dwarf can have only a certain maximum limiting mass. You cannot go beyond a certain mass, about 40% bigger than that of our sun, 1.4 solar masses. And this came to be known as the Chandrasekhar limit. And at that point, an uncontrolled runaway chain of nuclear reactions ensues.
But for decades, scientific investigators remained puzzled by just how this explosive chain reaction worked and what it looked like when it did. Computer models could never recreate what seemed to be happening in nature. But then in 2006, astrophysicists from the University of Chicago's prestigious Flash Center literally cracked the code. The Chicago team was the first to create a supercomputer program capable of processing the vast amounts of data. It had to be to simulate the complicated dynamics involved in the explosion of a whole star.
We call this extreme computing. The computers we use, some of them have 128,000 processors, so they're really 128,000 desktop computers all linked together.
Even with all that power, it took almost 60,000 hours of computing time. The astrophysicists decided not to start their simulated explosion exactly at the center of the star.
The reason that we decided to start slightly off-center rather than right at the center is that it's just very, very improbable that the flame will ignite exactly or even really close to the center. There's just no volume there. There's no there.
According to the remarkable simulation, in 1 second, a flame bubble forms inside the star.
So what you see right in the center of the star is the bubble rising quickly, growing, expanding as the burning takes place, and breaking through the surface of the star.
The molten bubble initially measures approximately 10 miles across, and rises more than 1,200 miles to the surface of the star.
It's spreading over the star at about 3,000 miles a second, and it collides at the opposite point on the surface of the star and produces extremely energetic jets. One that's moving outward at about 40,000 miles a second, and another jet that's punching in towards the star, and that ignites a detonation wave, which you've just seen race through the star.
Torrid temperatures, depicted using a standard color scale, reach an unfathomable 3 billion degrees Fahrenheit.
And you can see the moment it's just detonated, and going through the star takes less than half a second. The whole burning phase takes less than 3 seconds.
Expert analysis reveals that each Type 1a supernova is remarkably similar in size and brilliance.
This explosion is equivalent to completely detonating a mass the size of the sun.
This groundbreaking computer simulation illustrates for the first time how the explosions could occur in a Type 1a supernova. But Type 2s seem to be a radically different animal. By examining the stellar debris, scientists have reasoned that Type 2 supernovas are not the result of exploding white dwarfs, but rather the huge blasts of massive dying stars, at least 10 times the mass of the Sun. But how do these mega explosions work? The answer to the cosmic conundrum would come in the middle of the 20th century. That's when supernova gumshoes, for the first time in history, pounded the intergalactic pavements, systematically seeking gigantic exploding stars. Like detectives on a stakeout, cosmic investigators constantly scan the night sky. They're looking for the telltale bright lights that are evidence of a supernova. To carry out their surveillance, they use an impressive array of high-tech telescopes scattered across the globe.
Historically, we discover supernovae with ground-based telescopes, either scanning the sky constantly to look for new supernova explosions.
The cosmic supernova hunt began in the 1930s. Maverick astrophysicist Fritz Zwicky led the charge. He was the first to methodically search, catalog, and quantify new and exploding stars.
He was one of the real pioneers in finding exploding stars. And then he wanted to physically understand what they are.
The trailblazing astrophysicist proposed that these enormous and spectacular stellar events were the result of whole stars exploding.
Zwicky predicted that a certain kind of exploding star can occur when a massive star's core collapses and then rebounds, creating a colossal explosion. During the collapse, they said, a compact remnant should be formed, a ball of neutrons, a neutron star.
Essentially, the ordinary matter is made out of protons and neutrons and electrons. In this collapse of an iron core, the protons and the electrons that make up the iron atoms combine to make neutrons.
A neutron star is an incredibly dense object. Now, if you were to take a large building like the Empire State Building in New York and compress it to the density of a neutron star, it would be about the size of a marble.
They have a very high density. And in fact, a teaspoon of neutron star material would weigh as much as 1 billion tons on Earth.
Scientists today believe that only huge stars, at least 10 times the mass of the Sun, have the potential to generate this core collapse type explosion.
A massive star generates energy by fusing hydrogen to helium. It can fuse helium into carbon and oxygen, and it keeps on going all the way up to make iron. Iron is the most tightly bound nucleus. So when a star has made iron, it's really at the end of the line. and it's ready for disaster.
The iron core forms in the last day of the star's life.
And then it becomes so massive that essentially it collapses under its own weight. It just collapses gravitationally very quickly.
It takes less than a second for the core of the star to crunch down from something about the size of the Earth to a neutron star, which is maybe 10 or 15 miles across.
But this dense iron core doesn't settle down peacefully into its new life as a neutron star.
But instead of reaching an equilibrium configuration right away, the neutron star rebounds off of itself, just as the gymnast rebounds off of the trampoline and goes upward again. Well, this rebounding neutron star collides with the material surrounding it and imparts some of its energy to that colliding material, thus initiating an ejection.
However, unlike a gymnast for whom gravity ultimately prevails, pulling him back to Earth, in a core collapse scenario, something else continues to drive the ejection outward. The question became, what was this mysterious force driving the blast into space? Experts calculated that in order for a successful explosion to occur, one more ingredient was needed. They suspected something called neutrinos, ghostly energy-bearing particles that had been predicted but never observed. Astrophysicists believe that during a core collapse, when the electrons are pushed so close to protons in the nuclei of atoms that they combine to become neutrons, in the process, they release these tiny, mysterious neutrino particles.
The neutrinos are kind of interesting particles. They don't have any electric charge, so they don't interact with light. They only interact by what physicists call the weak force. And the weak force is aptly named. It means that these particles can go right through the Earth. They can go through long chunks of matter. So they're like ghosts. They just go through things.
For centuries, modern astronomers had been studying the remnants of supernovas in faraway galaxies from the distant past. But in 1987, they would get a front row seat to an explosion of their very own.
It was the brightest supernova seen in nearly 4 centuries, long after the development of the telescope, so we could use our full arsenal of equipment to study this fantastic blast.
In 1987, the most fantastic stellar event near our galaxy since the invention of the telescope occurred. The first to witness it was young Chilean astronomer Oscar Duhalde. His and astronomy's good fortune came on the night of February 23, 1987.
A telescope operator at the Las Campanas observatories, Oscar Duhalde, put water on for coffee and went outside to take a look at the sky. And when Oscar went out there, he looked at the Large Magellanic Cloud, which he knows very well, and he noticed that there was an extra star.
So he discovered this supernova explosion while basically running outside the telescope building and saw it with his own eyes.
When a star explodes, astrophysicists, like investigators looking for clues to a crime, know that the first few hours after the stellar death are the most critical. So in 1987, when the closest supernova in nearly 400 years appeared, they knew they had to act fast.
It was only about 170,000 light years away, a mere stone's throw for an astronomer. Supernova 1987A was in a small galaxy called the Large Magellanic Cloud, a dwarf galaxy that orbits around our much bigger Milky Way galaxy.
Being the first supernova of that year, the exceptional and nearby exploding star was simply labeled SN 1987A. But this time, dozens of seasoned astronomers all over the planet were ready for action. Armed with sophisticated tools and telescopes, they turned their minds and machines to the heavens and closely scrutinized Supernova 1987A. Knowing that an exploding star is at its hottest in the first few hours and is emitting lots of light in ultraviolet wavelengths, the astral detectives sprung into action.
At the time of the explosion, we saw the fastest moving stuff was coming toward us at 1/10 of the speed of light. So that was the actual star blowing up.
Scientists had their explosion. Now they wanted to know the name of the victim. They dug through a catalog that lists all known stars and their positions in the sky when they struck pay dirt. They found the star that exploded. It was tagged SK69202. They also determined that it was a huge star, 20 times the mass of the Sun. Examining the spectral evidence, scientists could see strong lines of hydrogen. SN 1987A bore the hallmarks of a Type II core collapse supernova. But to confirm their suspicions and prove the core collapse theories, experts had to have one more piece of physical evidence. They needed neutrinos, those ghostly particles that scientists predicted would be unleashed during the blast. In the early 1980s, scientists had built a handful of neutrino detectors around the world. They consisted of tanks deep underground filled with tons of pure water. But these detectors had yet to capture a single supernova neutrino.
We've had this story for a long time that most of the energy of a supernova explosion, a core collapse supernova explosion, goes into neutrinos, but we'd never seen those neutrinos.
As luck would have it, on February 23, 1987, they got their neutrinos. Two detectors, one beneath the city of Kamika, Japan, and the other under Lake Erie in Ohio, captured a dozen of the elusive particles.
There were light detectors on this volume of water that were used to see this little flash caused by the neutrino interacting with matter inside the tank.
For the first time ever, scientists on Earth saw tangible evidence of the mysterious neutrino particles generated in the core of an exploding star. Astronomers now knew the theories first proposed in the 1930s were right.
Supernova 1987A showed beyond a shadow of a doubt that the massive iron core of a very massive star collapsed and formed a neutron star, because in that process, a lot of neutrinos should be emitted.
With the deployment of powerful space-based telescopes, astronomers today have built on the astonishing discoveries made in the wake of Supernova 1987A. In 2006, 30-year-old astronomer Robert Quimby would once again turn conventional thinking on its head and revolutionize the way astronomers searched for supernovas.
Most supernova searches, they just want to find as many supernovas as possible, so they'll look once every 2 weeks, every 1 week, just so you can find them and so you can look at as many fields as possible and get as many supernovas as possible. So I decided to look at a limited number of fields and look at them as often as I can.
The enterprising cosmic gumshoe programmed his robotic telescope to systematically sweep the targeted field every night. Like an interstellar searchlight, it honed in on and methodically scanned the same small dark corner of the cosmos, looking for supernova suspects.
I had software that can very quickly process the data and tell me if there's anything there that wasn't there before. And when that happens, if I think it could be a supernova, I'll get a spectrum of it. And then that spectrum of it will tell me exactly what it is. Is it a supernova? What type is it? Etc.
On September 18th, 2006, Quimby got his big break. He found the brightest supernova ever.
And this is my fourth supernova. I didn't think that I should be so lucky. And others looked at the spectra and they started taking their own measurements of the photometry, how bright it was. And they figured out that, in fact, 2006 GY was brighter than any other published supernova.
Very slowly. Took over 2 months, 70 days to get the maximum light and then faded again. So it was a supernova unlike anything we'd ever seen before, discovered by this fourth-year graduate student at the University of Texas.
Analysis of the remnant indicated that the star, before it exploded, was 100 times the size of the sun. And with lots of hydrogen showing in its spectrum, the brightest supernova ever recorded bore the stamp of a Type II event. Then Quimby topped himself. When he finally analyzed a seemingly insignificant supernova he found earlier, called SN 2005 AP, he made a stunning discovery.
It was something like 100 billion times as bright as the sun. As compared to, for a Type 1a supernova, the peak may be only 6 billion times as bright as the sun.
It was even brighter than SN 2006 GY. Like circumstantial evidence, astonishing discoveries of new ultra-bright supernovas like 2005 AP and others have opened up a whole new avenue of inquiry into exploding stars and their MO.
The basic idea we have is that perhaps this is connected somehow to gamma ray bursts.
Gamma rays are the most powerful form of light known in the universe. By analyzing supernovas, investigators are getting closer than ever to solving some of the most confounding riddles in the cosmos.
How one of them makes gamma rays and the other makes an ordinary supernova is still one of the big mysteries. Nobody really knows how that works.
What astronomers do know is that supernovas and the gamma ray bursts associated with them are the brightest beacons in the universe. On the galactic highway that is the cosmos, supernovas serve as celestial signposts, pointing astronomers to the beginning and the end of time and space. NASA's powerful SWIFT satellite, launched in 2004, was designed specifically to sweep the sky and detect gamma ray bursts in the universe. Like cosmic first responders, astrophysicists at NASA's Goddard Space Flight Center in Baltimore, Maryland, are standing by 24/7, waiting for a 911 call from SWIFT.
Basically, less than 2 minutes after SWIFT discovered a gamma ray burst, the satellite sends down emails directly to our blackberries.
When a recent supernova, recorded as SN 2006 AJ, appeared, the SWIFT satellite caught the shocking gamma rays it generated.
And that gamma ray burst was very interesting because, first of all, it was a very long-duration gamma ray burst. Usually gamma ray bursts are very short-lived phenomena, only fractions of a second or a few seconds. But this gamma ray burst was visible for like 35 minutes. We saw 3 days later a supernova explosion going off at the exact same location. And this solved one of the important mysteries of gamma ray bursts, because we found out that at least parts of gamma ray bursts are due to massive stars that are exploding.
Astronomers today can see hundreds of supernovas and the deadly gamma ray bursts they generate. On the cosmic highway, scientists use these stellar headlights to ascertain the bounds and breadth of the universe.
You can use supernova to probe the universe because if they're very dim, you know they were very far away, and then you can study the curvature of space-time and all of the cosmology that you can study with them.
For example, if you're on a desert highway and you're looking out at the lights of the cars, you can tell which are nearby and which are far away from the apparent brightness of the lights. The ones that are nearby look bright, the ones that are far away look dim.
Measuring how far away things are very systematically will tell you about the size, the age, the shape, the history, the future of the universe.
It turns out that Type 1a supernovas are the best suited for this purpose.
One of the things that's really interesting about the Type 1a supernovae, the ones that are exploding white dwarfs, is that there is this fixed mass, this Chandrasekhar mass, that sets how big the explosion is, how much stuff is involved. And the consequence of that is that many of these have very nearly the same brightness. If the explosion produces the same amount of light, then we can measure how much light we see and figure out how far away the supernova is.
This is known as the standard candle principle.
Type 1a supernovae are like standard candles. They all have about the same peak power, the same peak luminosity. So if you look at them from different distances, they appear different apparent brightnesses. They look dimmer if they're farther away and brighter if they're more nearby. So if we find Type 1a supernovae in distant galaxies and measure their apparent brightness and compare that with the known power of a nearby Type 1a supernova, we can determine the distance of that supernova and hence of the galaxy in which it's located.
The trailblazing technique has also led astro-investigators to some radical conclusions.
Basically, you can use the distances to supernovae to figure out what the universe is doing, how old it is, and we now know that from various lines of evidence that it's a little less than 14 billion years old. But in particular, found out the universe was accelerating when we thought it was decelerating in the grip of the gravitational materials in it. That's just caused an intellectual revolution, like throwing a ball up towards the ceiling, and rather than having it come back down into your hand, it goes faster and faster and faster towards the ceiling. It's completely counterintuitive.
Basically, all the astronomy textbooks out there all said that the universe should be decelerating. That is, gravity should be slowing down the expansion rate. But what this result showed is that instead of slowing down, it was actually expanding faster and faster and faster.
While the examination of supernovas has helped scientists unravel many monumental cosmic mysteries, experts believe that if they continue to follow the clues left behind when huge stars explode, they'll be able to answer the biggest unanswered questions. Today, scientists know that someday soon, we could each witness for ourselves the marvelous and almighty force of a supernova.
Our galaxy is 100,000 light years across, so that means there's light from 1,000 supernovae that's on its way to us now.
It could even happen in our very own Milky Way.
In our galaxy, we are expected to have on average about 2 supernova explosions per century. The problem is that the last supernova that we saw in our galaxy is almost 400 years ago. So our galaxy is long overdue.
If it did happen in our own galaxy, we, like the titans of space and time, Tycho, Kepler, Chandrasekhar, and Zwicky, would bear witness to the most destructive and the most creative force in the universe, the supernova.